This week will be the last week for us to study equation of motion for solving a problem. In last 2 weeks, we studied in equation of motion, and we studied how to use equation of motion to solve a problem of translation. And in last week, we studied how to use it to solve a problem of rotation about a fixed axis. And in this week, we will continue this study, and we will study how to use equation of motion to solve a problem of general plane motion. And this will be much more difficult than what we studied in last 2 weeks. And also in this week, we will discuss particular problem that's friction rolling and similar problems. And we will study how to deal with this kind of problem. Okay. So firstly, I think it should be useful to watch a couple of videos to see the applications. First application here, and here you can see a soil compact, and our focus is the roller. Okay, so to design the shape of this roller, we have to make sure it has higher strength. But how to determine the strength and how to determine the loading on the shaft of this roller? And here you can see this roller should be undergoing general plane motion. Okay, there may be slipping between this roller and the ground, and there may be no slipping. Okay, so in this case here, I have a similar question as I asked in last week for this pin, for this shaft. So what should be the loading on this shaft? Should this loading on the shaft be equal to the gravitational force applied on the roller? So how do you think this? What should be the answer? Okay, so if in statics, if we talk about the loading on this roller, the loading on this shaft, it should be equal to the weight force on the roller plus the weight force of the vehicle. But in statics, when this soil compact is working and when this roller is rotating, the loading on the shaft of this roller should be much higher than that when the soil compact is in static. The reason is still because of the existence of acceleration. Okay, let's have a look at this video. when this soil compactor is working, and normally the working environment is very harsh, and because the road surface is rough, okay? So this can result in higher acceleration. So finally, higher loading on the shaft. Okay. And this is, okay, let me switch to my slide. Okay. So that is one application. Okay, next one. Okay, next one. In this one here, we will watch a video, and this video is about the crash of a vehicle. Okay, have a look. And our focus this time will be the dummy. Okay, the dummy in a vehicle. Have a look. Okay, let me play this video. Okay, this one. Okay, look at the dummy and what the motion this dummy is undergoing when crash happens. And compare one without seat belt and airbag, and another one with airbag and the belt. Okay, another video. Look at the passenger at the rear seat, belted and unbelted. Have a look how different they are.
It's a habit for most of us to buckle up while we're driving. But what about when we ride in the rear seat of someone else's car, or use Uber or Lyft? The Institute survey found that full-time belt use is lower in the rear seat. And that's especially true for people who primarily get around by taxi or ride-hailing service. Less than 60% of people who said they frequently take taxis or use ride-hailing services said they always wear their belt. People who reported buckling up less often were asked for their reasons. A quarter of respondents said they believe the rear seat is safer, so using a belt there is unnecessary. If you're not belted in the rear, you're putting yourself at risk, and you're also putting other people in the vehicle at risk. People belted in the front seat can be injured or killed by unbelted occupants in the rear flying forward in a crash. We recently conducted a test to show what can happen when there's a crash and the person in the back is unbuckled. In a simulated 35-mile-per-hour impact, the unbelted dummy slams into the back of the driver's seat, pushing the driver dummy into the deploying airbag and steering wheel. Drivers are twice as likely to be killed in crashes when the occupant behind them is unrestrained. All but one state requires adult front seat occupants to use safety belts, but rear seat passengers are covered by laws in only 29 states and DC. Only 20 have primary enforcement, which means a police officer can stop the motorist for the seatbelt violation alone. Stronger laws would help,
That's it. So to study the impact a passenger can have during crash, or design the seatbelt system, and this should be a problem. Dynamics can help. Okay. So now let's have a look how we can use these equations. So for general plan motion, as we studied before in last 2 weeks, we have 3 equations, okay? 3 equations. If we use x, y coordinate system, for the translation component, we have x and y is 2 components. For the rotational component, and we can use g, the mass center point, for our calculation. And in many cases, it may be more convenient to use a point P instead of the mass center point for calculating the rotational component. Okay. Now, I mentioned the problems of general plan motion can be more difficult than those of translation or rotation about a fixed axis. But why? Okay. Firstly, for translation, we studied this in the week before last week. In translation, the angular acceleration of a rigid body is always 0. So, for rotational components, if you use mass center point G for your calculation, then this is always 0. Next, for rotation about a fixed axis problem we studied in last week, if this rigid body undergoes rotation about a fixed axis 0.0, then you can easily find the acceleration at the mass center point G and the angular acceleration alpha. Okay, for AGT, the tangential component of AG, can be calculated using angular acceleration alpha. For AGN, this can be calculated using the angular velocity. So, if we use a normal tangent coordinate system, and then for the translation component, you can use alpha and omega in these 2 equations. Okay, you don't have an unknown AG because this can be related to omega and alpha. Now, let's have a comparison. So, in translation component, the angular acceleration alpha always 0. In a problem of rotation about a fixed axis, alpha can be related to AG. But in a problem of general plan motion, in many cases, you can easily define the relationship between alpha and AG. So this means in many problems, acceleration analysis has to be adopted. So this will increase the difficulty when you solve problem. But there exist various situations, and we will look at these various situations. So let's have a look at this first example. Try to define this problem. In this problem here, there is a uniform bar, and initially it was at rest, okay? Because there are two codes. One is CA and another one is DB, these two codes, to hold this uniform bar. If we cut this code CA, what will happen? This uniform bar will lose the balance, okay? So this means if we cut this code CA, this bar will have an acceleration. The target here is to determine a tension force in code DB, and the angular acceleration of this bar AB. Immediately after AC, code AC is cut. Immediately after AC is cut, this means we will be focusing on an instant, and that instant we have already got an acceleration on this bar AB, but at this instant for bar AB, its velocity is still 0. Okay, we focus on this instant. To solve this problem, after defining this problem, and we will need to present the free body diagram and kinetic diagram. Okay, now let's see how to draw this diagram. So firstly, I will draw the free body diagram. And this will be free body diagram. And here it will be kinetic diagram. Okay, so in this free body diagram, we need to indicate all the external forces. Okay. But what external forces we should include? At the mass center point G, we should have weight force W. Another external force is here. At point B, we still have a tension force from the code. So this will be T. No other external forces at this instant. For point A, because at this instant, the code CA is already cut, so no tension force at point A. Kinetic diagram. In this kinetic diagram, so firstly, you can see I have already defined an X, Y coordinate system, and in this one here, I assume counterclockwise is my positive rotation direction. Okay. So in this one here, in this kinetic diagram, I assume alpha is positive counterclockwise. Okay. I don't know the acceleration at point G, so I just assume AGY, AGX positive. At this moment, I don't know the relationship between alpha and AG. Okay, so at this moment, alpha and AG, these two are independent. Okay, now let's go back to this solution. Okay, here is the solution. In this solution here, I already defined this problem, and I have drawn the free body diagram, and this kinetic diagram. I know the mass of this uniform bar is 50 kilo. Don't know alpha, don't know T, don't know AG. Okay, as I mentioned, AG and alpha, at this moment they are independent, and we just assume they all are positive. Now, we will try to use these three equations to solve this problem. And the first thing is to calculate the MMI of this bar, and this should be an easy task because it's a uniform bar, and we know M, we know L, so we can calculate using the established equation. Okay. Now, first equation is about the translation component along x direction. Along x direction, if you look at this free body diagram, you can see along x direction, no any external force. So it's 0. So this means we can work out AGX directly. It should be 0 at this moment. For translation component along y direction, we can establish our second equation. And in this one here, in the free body diagram, you can see T is upward, so it should be positive, and W is negative, so we give a negative sign before W. We already know W. And then, finally, we have this second equation, and in this one here, we have T, we have AGY, these two unknown. Okay, now for the third equation. For the third equation, obviously, we can select point G for our calculation. Okay, so look at the diagram. If we calculate the rotational component about point G, then W, the moment arm, is 0. We only consider the moment generated by T. T about G, this generated moment should be counterclockwise, so it should be positive. Okay, so no negative sign before this item. On the right side, for the kinetic moment, if the calculation is about point G, then we only have I, G, alpha, okay? So now we have our third equation. And in this one here, we have T, we have alpha. For this third equation, if you like, you of course can use another point to do your calculation. For example, using point B for your calculation. Okay, using point B for your calculation. And this time, on the left side, we will need to calculate the moment generated by the weight force W about B. Okay, again, this is counterclockwise, and this should be positive. But you can see here, if you use point B for your calculation, actually the calculation is a little bit more complicated. But finally, you will get your third equation. Okay, for the third equation, 3 and 3 prime, you only need one. Okay, one of them will be sufficient. Now, if we look at the equations we have worked out, we can see we have now equation 2 and equation 3 or equation 3 prime. Whatever, we have T, AGY, and alpha. We have 3 unknowns. We only have 2 equations to use for equations now, but 3 unknown parameters we can't solve. Why we can't solve? Because for A, G, and alpha, we don't know their relationships. So, to solve this problem, we have to find the relationship between A, G, and alpha. But how to do? We have to involve acceleration analysis. Okay, now, to do acceleration analysis, and this will be the knowledge we studied in week 3. Okay, for acceleration analysis, you know, we must have kinematic diagram. Okay, and this kinematic diagram is for this bar AB. And for acceleration analysis, you know, we have to select 2 points for our analysis. And in this problem here, G is the mass center point, and B is the point connecting to the code AB. So it looks like we only have these 2 points for analysis. Now, kinematic diagram. In this kinematic diagram, we still use the directions indicated in the kinetic diagram. Alpha counterclockwise, AGY, AGX, these 2 we assume positive. Okay, we have to keep consistency when we do acceleration analysis. Alpha, AGY, AGX, this must be as same as what we indicated in the kinetic diagram. Okay, now for another point, point B is unknown. And in this diagram, we still can assume these 2 are positive. Okay, and again, for the coordinate system, it's still the X, Y coordinate system, and we define counterclockwise as a positive direction. Now, for acceleration analysis, you know, we only have one equation involving 2 points, G and B. And in my expression here, I put G on the left side, and B on the right side. Okay. So this is vector calculation. Okay. And for AG, we have AGX and AGY. AGY, we don't know. But for AGX, from equation 1, we already know AGX is 0. Okay. Now, look at the right side. On the right side, we don't know ABX. But how about ABY? For ABY, look at this problem. Okay, look at the problem. In this one here, you will see for B, at this instant, ABY on this bar AB is ABY. At this instant, because this bar AB is still horizontal, and this code DB is vertical. So this means ABY on this bar AB should be equal to ABN on this code. Okay, because B is the connection point between this code and the bar. So the acceleration ABY should be equal to ABN on this code BD. Now, go back to this solution. If ABY on AB is equal to ABN on code DB, then how to calculate ABN? We can use the knowledge we studied in particle dynamics. Okay? Because the point B on the code DB, B will be undergoing a rotation about a point, the center point is at point D. Okay? So B will be rotating about the center point D. Then ABN can be calculated using this equation. This equation here, VB is the velocity at point B on the code DB. Rho B slash D, that's the distance from B to D. Okay. Because of the tension force in the code DB, so the distance from B to D can be easily determined. Whatever, because VB at this moment, the velocity of point B at this instant is 0. So finally, ABN must be 0. If ABN must be 0, then that means ABY on AB should be 0. So here, for ABY, we can determine it should be 0 in this equation. Okay. Now, in this one here, because omega at this moment is 0, so this last item should be 0. Now look at this vector equation, and now we have AGY ABX, and alpha is 3 equations. And you know from one vector equation in planar kinematics, from one vector equation, we can establish 2 scalar equations. So in this one here, you will see, we can find ABX, this one is 0, okay? And we can also work out the relationship between A, G, Y, and alpha. And this is what we want. And that will be our 4th equation. Because if we know A, G, Y, and alpha, if we know their relationship, then look at this equation here. For 2 and 3, these 2 equations, we can substitute the relationship between A, G, Y, and alpha. So finally, we will have only 2 unknown parameters and 2 equations. So we can solve this problem. We can solve alpha, we can solve A, G, Y. And also we can work out tension force T in the code BD. Okay? And that's the solution of this problem. Do you have any questions? Any questions? So comparing to the solutions to the problems in last 2 weeks, and you will see, to solve a problem of general plane motion using equation of motion, because acceleration analysis has to be involved in many cases, so it will be more difficult. Any questions? Okay, if no questions, let's go back to the slide. Okay, so next we will study another kind of problems, and this is a so-called particular type of problem. And this kind of problem will be easier for us to solve. In this kind of problem, we involve a uniform cylinder or a body of a circular shape. Okay. Whatever the mass center point G of this uniform cylinder or a body of circular shape, the mass center point G must coincide with the circle center. And this is a problem of rolling without a slip. If it's a rolling without a slip problem, when we calculate the rotational component in the equation of motion, we may select the instantaneous center of zero velocity, and then we can get an equation like this. But why? Have a look. Okay, here is a roller of a soil compact, and we know when it's walking, it's undergoing a general plane motion. Okay. If we assume at this contact point A, no slipping occurs, And if we calculate the rotation component using this point A, what will happen? We will have two items on the right side in this equation for kinetic moment. Look at this diagram, kinetic diagram. And here we have AG and we have alpha. If we calculate a kinetic moment about point A, we have two items. One is IG alpha, and another one is kinetic moment generated by MAG about A. Okay? And this can be simplified, and finally we get IA alpha. We can rearrange the right side in this equation. And when we rearrange this, we will need this equation. AG, actually AGX, because in this case here you can see AGY should be 0, okay? So we only have AGX. AGX is equal to alpha times the distance from G to A. Why we have this? Have a look. Probably you still remember this. We studied acceleration of a rolling without slipping. In this case, we have the conclusion AG is equal to alpha times the distance from G to A, okay? And in this one here, this AG is actually AGX. If you don't remember this, probably you can refer back to what we studied in week 3. Okay, so what does this mean? This means this kind of a problem will be as similar as the problem we studied in last week. In last week, we studied rotation about a fixed axis. And in this particular type of problem here, because we have a Nice point, and this is also a rolling without a slipping problem, we have a Nice point, for example, here is point A. So this problem, the solution will be as similar as the solution we used in last week for rotation about a fixed axis problem. Now, let's have a look how to